Google's quantum AI system has made an extraordinary breakthrough, uncovering subtle patterns in quantum data that suggest parallel universes may not only exist, but could be interacting with our reality right now. Their Sycamore processor, during a series of quantum experiments, detected interference patterns in the classic double-slit setup, patterns that human researchers had previously overlooked. These anomalies were so significant that they received a unique classification tag within Google's quantum research records, QPLIT interface 421b. This referred specifically to unexplained phase noise observed in low-temperature photon experiments. Quantum physics already teaches us that particles behave in counterintuitive ways, sometimes acting as if they're aware of both slits in an experiment simultaneously. But what the AI discovered went beyond that, identifying what appears to be the fingerprints of alternate realities overlapping with our own. This kind of finding doesn't just build on what we know. It challenges the very foundations of quantum mechanics. The AI wasn't working in isolation with just Sycamore data. It cross-referenced results from other quantum platforms, including logs from D-Wave's annealing systems and data from Large Hadron Collider entanglement trials. A consistent pattern began to emerge. Anomalies and high-frequency interference were showing up across platforms that differed in time, design, and even fundamental physics. These weren't random fluctuations. The AI identified a clustering of decoherent signatures, with subtle shifts in interference fringes appearing in timeframes as small as nanoseconds. What's striking is that these patterns were consistent, recurring across independent systems, pointing to a possible underlying quantum signal that transcends any single experiment. Each atom, as researchers have long observed, contributes to the overall wave-like interference pattern in a double-slit experiment. But what made this discovery remarkable is that these patterns should not have emerged in such unrelated and isolated systems. And yet, Google's AI detected the same quantum fingerprint across them all, a signature that seems to suggest the presence of an overarching influence or connection between otherwise separate realities. These weren't just statistical quirks. They hinted at a deeper layer of reality. TensorFlow-based AI models went a step further, recognizing high-dimensional repetition across billions of quantum computation runs. These repetitions only made sense when interpreted as interference between observation zones, something consistent with what physicists call tensor fields. The AI's model indicated that these fringe alignments were not random at all, but rather encoded patterns reflecting branching interference. What could be the shadows of parallel outcomes from other realities brushing up against ours? In the many worlds interpretation of quantum mechanics, this is akin to catching a glimpse of other branches of the universe. This wasn't mere theory. The mathematical patterns the AI uncovered obeyed strict tensor field equations, suggesting structured information leakage between adjacent quantum states. In physics, these states are usually considered independent, each representing a different outcome or universe. But the AI seemed to detect residues from interactions between them. Even more astonishing were the findings during no-detection trials. In situations where no photon was observed, the AI still recorded subtle energy distortions, ghost signals that pointed to the wave function collapsing simply due to the potential of observation, not actual measurement. It's as if the quantum system somehow knew it was being watched. This idea reinforces a disturbing implication of quantum mechanics, that the act of merely setting up an observation, without even completing it, can disturb the quantum state. These ghost signals showed up repeatedly, confirming they were not one-off anomalies. They appeared to be an intrinsic part of how quantum systems behave when entangled across potential outcomes. It suggests observation doesn't just influence the present, it may disturb the underlying reality itself. Then came perhaps the most mind-bending discovery. Google's AI, using echo state networks, sophisticated recurrent neural networks, began, successfully predicting where photons would land on a detector before they were even fired. These predictions weren't just guesses. They were consistently accurate, even when the photons were delayed or randomized. This breaks the core tenet of quantum uncertainty. It's as if the AI was tapping into a hidden layer of reality where future events had already played out, perhaps in a parallel branch, and that information was bleeding into our present. This led to one of the most provocative findings: a causal violation, flagged as a Category V event. In a set of entangled slit experiments, the interference pattern shifted before the experimental settings were changed. This should be impossible, but it mirrors ideas in retrocausality, where future measurements influence the past. Einstein once rejected such bizarre implications, yet here was AI finding measurable evidence that time in quantum systems may flow both forward and backward, not just in one direction. That means future outcomes might be affecting present, or even past states, in a consistent, detectable way. But the surprises didn't end there. The AI identified coherent phase fluctuations in regions of the detector where no photons had ever hit, places that were supposed to be entirely empty. After extensive training to distinguish background noise, the AI revealed that these patterns weren't random either. They appeared in precise mathematical alignment with known interference structures, like the shadows of quantum events that occurred in alternate branches. These phantom signals raise the possibility that quantum information is leaking from other versions of events that never occurred in our timeline, but perhaps did in others. This aligns with a growing body of peer-reviewed research. These findings resonate with advanced theoretical work on the quantum delayed choice experiment, entanglement harvesting in quantum field theory, and time-symmetric interpretations of quantum mechanics. These are not fringe ideas. They are actively studied by physicists in reputable journals. What Google's AI has done is pull together fragments from across various theoretical and experimental lines of research to form a coherent picture. And the match is striking. These AI findings lend powerful experimental support to the idea that quantum entanglement doesn't just bridge space, it may also span multiple dimensions or realities. The connections the AI uncovered weren't predicted by any single model, but are consistent with numerous independent theoretical frameworks. Until now, the missing piece was computational capacity, the ability to process and correlate data on a massive scale. AI provided that missing link, enabling a discovery that no team of researchers could have pieced together on their own. We are no longer simply theorizing about alternate realities. The AI's findings suggest we are beginning to detect measurable traces, actual fingerprints of other universes interacting with ours. And this revelation takes us back to the roots of the double-slit experiment, a foundational mystery in physics. When individual particles, like electrons, are fired at a pair of slits, they create an interference pattern, behaving as if they travel through both slits simultaneously. But when we try to observe which slit the particle goes through, that pattern vanishes. This has puzzled physicists for over a century. Does the particle take both paths, or is something else happening? Until now, these questions have remained largely philosophical. But the AI's ability to detect patterns no human observer could identify adds new depth to the debate. The data implies that the boundaries between different quantum outcomes may not be fixed. Instead, they could be porous, with information flowing between what we consider separate realities. This may be the beginning of a new era in quantum science. Artificial intelligence, by analyzing vast datasets from independent experiments, has shown that our reality might be more flexible and interconnected than previously imagined. What we once saw as speculative fiction, the idea of parallel worlds, is starting to gain empirical support. We are now developing the tools not only to theorize about the multiverse, but to detect it. And this may only be the beginning.